As I mentioned, today is Logan Paul's qualifying exam presentation, and the PhD students who have not done the qualifier yet, hopefully this will be a good model for what you have coming. Logan has been a member of my lab now for about 2 years. He actually did his undergraduate degree in computer science here at MSU, finished his master's in computer science last May. Now is marching along on his PhD. He already has, what, 4 publications related to this? So, with that, the topic of his research and of the qualifier is continuous time Bayesian networks, continuing along the line of the work that Lisa Droid did as part of his dissertation. So with that, let's call the work.
Okay, I'll get started. Great, I'm Logan Paul. I'm here to talk about my research, and before I do, I'm going to give you a little bit of motivation. So consider a space shuttle. It's a complex system, and it's got many faults that might occur, and these faults change as time evolves. So as time goes on, one component may end up failing, and that failure may in turn cause other failures in the system to occur. And this ends up cascading, so these effects cascade down the line. What we'd like to be able to do is actually model the system so that we can determine which components are likely to fail. If failure occurs, are we likely to see other related failures? And if we're actually able to model this, we might be able to improve the system as a whole, or even predict faults before they occur and end up preventing them altogether. So that is what my research is involved in. I look at dynamical systems. There are systems that change over time, so these faults are going in and out of particular states. And the way I'm going to do this is I'm going to use continuous time Bayesian networks to model the systems. I'm going to talk to you today about 5 different journal articles. That's what's required for the qualifier, and it was easy enough to pick these 5 since they're the only 5 journal articles in CTBN literature. So those are the 5 I picked. The first one is going to be a tutorial on CTBNs as a whole. It's actually structured Markov processes, which are a more general model. And then the next 2 are going to be, we've got mean field variational approximation and importance sampling. These are 2 inference algorithms for continuous time Bayesian networks. That's going to allow us to perform queries on the networks. And then the last 2, written by our very own Leisman Sturluson. We've got uncertain and negative evidence. This is a paper where it's going to describe the various types of evidence we can apply before performing inference. And then we also have a paper on sensitivity analysis, which is going to allow us to determine how variations in the input are going to affect the model. So this is going to help us out in the learning process. We'll take a look at that a little bit more later. So before we can get into the first paper, I'm going to give you just a little bit of background on Bayesian networks, because a lot of the information that I'm going to give you about continuous time Bayesian networks is based on some of these concepts. So the idea of a Bayesian network is what we'd like to do is we'd like to model a probability distribution over the state of the system. And the concern is that the full joint probability distribution is going to be exponential in the number of variables in the system. So this becomes quickly intractable, and we end up not being able to reason over any models that are of any interesting size. So a Bayesian network gets around this by factoring the variables in the system using a directed acyclic graph. So the nodes in this graph are going to represent your variables, and the edges are going to represent conditional dependencies between these variables. And so what we end up with is a full joint probability distribution where we factored it by node, where you've got the node conditioned on the parents in the graph. And what we end up with is this graph structure plus the parameterization for the nodes. So where the original structure was exponential in the number of variables, we're actually going to parameterize each node individually, where we've got conditional probability tables, and we enter probabilities into this table that is exponential in the number of parents for the node rather than the number of variables for the whole system. Here is an example of a Bayesian network. So we've got cloudy as a node, and this can have 2 different states. It's either cloudy or it isn't. And then sprinkler and rain depend on cloudy. So this is the notion that it's more likely to rain if it's cloudy, and you're less likely to turn your sprinkler on if it's cloudy as well. And then what we've got at the very bottom is the notion of grass being wet is dependent on whether the sprinkler was on and whether it was raining. And so we can infer over this network and collect information given evidence that we apply. For cloudy, we've got the conditional probability table we see up top, and because it has no parents, we've just got the probability of it not being cloudy and it being cloudy. C equals F and C equals T for true and false. And then for rain, because rain has a parent, we've got the same thing. We've got the probability of it being false and true, but we've got that for each state instantiation of its parents. So we've got that in the event that it is cloudy and in the event it isn't. So this is great. It's fantastic that we're able to factor this full joint probability distribution, and we're actually able to work with these models now, but we're going to get a little greedy, and we're going to say we want even more. We'd like to be able to say, okay, that's great if it's a static system, but what if it's a continually changing system? We'd like to be able to reason about the past, the present, and the future in that case. And so what we'd like to do is we'd like to reason about probabilities over time. So Bayesian networks are going to be considered static models where the probabilities are just these series of values. We saw there was a 0.5 chance of it being false and a 0.5 chance of it being true, and that is our distribution. With a continuous time model, we're actually going to be looking at probabilities of variables as functions. So now we're looking at maybe a continuous or a discrete function that actually provides these values as a function of another variable. And for us, we're going to be looking at time as a variable. So as a function of time, we're going to be changing the probability. Okay, with that background out of the way, we're actually able to get into our first paper. Again, this is a background. We're going to spend most of our time on this paper because it's going to give you the information you're going to need to understand the remaining papers. But this one's going to be a tutorial on structured continuous time Markov processes. And a continuous time Bayesian network is a continuous time Markov process. So let's start by actually describing what this paper did. First, they argued for the use of continuous time. We'll see here in a second. You can also model time discretely. Then they discuss continuous time Markov processes as a whole. And then they introduce three specific models that are structured continuous time Markov processes. Specifically, they're going to look at Kronecker algebra, which factors continuous time Markov process using matrix operations. Then they've got a decision diagram, which uses an index function that's encoded over a decision tree to model back to the original continuous time Markov process. And then finally, they looked at continuous time Bayesian networks. For the sake of time, we're only going to focus on continuous time Bayesian networks since that's what we're going to be looking on throughout the rest of the presentation. So before we get there, we're going to talk about discrete versus continuous time. So discrete time requires you to actually select the time granularity. And this doesn't maybe seem like an issue, but consider, for example, that events occur every hour on the hour, except one time they occur in between 2 minutes. Well, at that point, you have to select a time granularity that equates to the smallest spacing between your events, which means that you're going to have to end up breaking this down by the minute. And so you have to discretely model each time step by the minute. And the concern here is that we've kind of overrepresented the system that we need. So everything's happening on the hour, except for this one time there was space in between the minutes. So we've got all these minutes where nothing's changing, but we're still modeling them directly. So it's almost overly powerful. The dynamic Bayesian network is an example of such a discrete system. What we'd like to look at is models that actually model time directly. So if we include time as part of our model, what we can do is we can index to the exact point that we need. So if everything happens on the hour, except for that one time, what we can do is we can say, let's go straight to that hour, and then the next hour, and then the next hour, and then that next minute. And we can do that directly without having to look at every single minute in between. Continuous time Bayesian networks are an example of these models. So, we're going to define a continuous time Markov process to be consisting of two different components. it's going to have an initial distribution of the variables and the states of the system, and it's also going to have a single intensity matrix we're going to call Q. And what it's going to do is it's going to describe the continuous evolution of the various states of your system, and these are discrete states, and it's going to satisfy the Markov assumption. So regardless of where we are in time, the behavior in terms of transitioning between states is going to remain the same. The concern here is that it's going to be exponential in the number of variables of the system, and we'll see that in just a second. So here is an example. Hopefully this clears some of that last slide up. At the top, we've got our initial probability distribution. And so this is the probability of being in each state of the system at the beginning of the process. And then we're going to have Q is going to be our intensity matrix, and it's going to define how the system transitions between states throughout the process. And so Q, let's say 1, 2, defines the behavior for transitioning from state x1 to state x2. So if you're currently in state x1, you're going to end up transitioning to x2 with a rate of q12. We say rate because what these are is they're actually defining exponential distributions. So we've got an exponential distribution on the bottom here, and the elements in your matrix are actually describing the rate parameter for your exponential distribution that's going to define how long you expect it to take to transition from one state to the next. Each variable in the columns are going to dictate how long it's going to take for you to transition to each other state, and the diagonals of the system are going to be defined as the negative sum of the remaining portion of the rows, and what that's going to do is it's going to define your sojourn time. So it's how long you expect to stay in x1 before transitioning to any other state. And so that's what's going to happen there. Unfortunately, because this matrix and the initial probability distribution are exponential in the number of variables, we can't work with very large models. So what we're going to have to do is, just like a Bayesian network, we're going to have to factor it. And so we get to continuous time Bayesian networks, the crux of this presentation. We're going to factor it with a graph structure G. The nodes are going to be variables, and the arcs between the nodes are going to represent conditional dependencies, so this should sound pretty familiar. And the parameters for each node in this case, instead of using the conditional probability table, we're actually going to be defining smaller Markov processes. So we're going to factor the Markov processes. So each node is going to have an initial distribution associated with just the states of that node and a set of conditional intensity matrices. This is an intensity matrix just like before, but it's going to be just over the states of the node, and we're going to have one for each state instantiation of the parents. So it's going to factor this conditional Markov process just like a Bayesian network factors a full joint intensity matrix, or sorry, a full joint probability distribution. And what we're going to do is we're going to end up losing a little bit of representational power. Specifically, what we're losing here is that it's going to disallow simultaneous transitions just because of how we end up factoring this thing. And that makes enough sense. We're going to allow that assumption just because in continuous time, the probability of two variables transitioning at the exact same time ends up going to 0 because time is continuous. So this is going to end up mitigating our exponential blowup, and we can now work with larger models. Here is an example of a time Bayesian network. So this is called the drug effect network. It's attempting to model how a particular drug, when taken, is going to affect the various behaviors of a person's body. So uptake is when the drug is actually working. It's going to affect the concentration of the drug. The concentration of the drug is in turn going to affect how drowsy you are and how much joint pain you have. So supposedly this drug is supposed to reduce joint pain, but it might have the side effect that it makes you drowsy. Your joint pain isn't just affected by concentration, it's also affected by the barometric pressure, and the concentration of the drug isn't just affected by its uptake, it's also affected by how full your stomach is, which is in turn affected by whether or not you've been eating, which is in turn affected by how hungry you are, which again cycles, and is in turn affected by how full your stomach is. Now that's actually interesting. What you'll see is there's a cycle there. The Bayesian network does not allow for cycles, but because we're working with continuous time, we're actually going to allow them in this network. Just to look at a specific example, we're going to look at the joint pain subnetwork. So if you remember the joint pain network, or the joint pain node, its parents were the barometric pressure and the concentration of the drug. Those are the two things that are going to affect your joint pain. And so because this node has two parents, and each of those parents has two states, we're going to end up with 2 to the 2, we end up with 4 different intensity matrices. So these are conditional intensity matrices conditioned on the parents of this node. So we can actually determine the behavior of joint pain in the event that barometer is in state B2 and concentration is in C1. Then we see in the bottom left the probability given B2 and C1. We end up seeing that this bottom left matrix here is going to be the behavior of joint pain given its parents in those states. These are 2 by 2 matrices because joint pain is itself a variable of 2 different states. We can see that the parameters are actually going to be different for each of these nodes, so you can expect that the behavior of the node is going to change based on its parent states. So this paper gave a summary of continuous time Markov processes and provided an analysis of the various ways to structure these continuous time Markov processes so they end up being feasible. And in terms of open questions they left us with, they talked about how CPNs have not yet been extended to continuous state. We've been talking about discrete state here, but there are potential avenues for extending this continuous state as well, although it will be at the cost of computational complexity. And it also discusses approximate learning using statistical testing. So in CPDMs, the learning method uses a graph scoring function, but there are methods for using statistical testing that have been used in Bayesian networks that just haven't been moved over to the continuous time Bayesian network side of things. So those are a couple questions they left open. And with that, we'll move on to the next couple papers. So as a reminder, these next couple papers are going to be talking about inference. We now have all the background information we need to understand the model. We're just going to talk about how we can actually use the model now that we've got it. So the first one we're going to talk about is the mean field approximation, and I'm going to talk to you just a little bit about inference before we get to it. So inference as a whole, the notion is you're going to apply some evidence. So you can inform the model. You can basically tell the model, okay, I actually know some things about the system already. I know that this particular variable was in this state. I know how long it was in that state. I know this other variable transitioned at this time. And you can basically apply that information. And then once it's been applied, you can then perform inference to ask questions about other variables that you don't know the states of. So let's say you know the state of a variable for a period of time. If you want to know about its state after that period of time that you've actually observed, or maybe you're interested in the state of a variable that you haven't observed at all. This problem with inference is actually very difficult. It's been shown to be NP hard by Leisman. So it is, in fact, exact and approximate inference are both NP hard. So this is going to be a difficult problem we're trying to solve here. This is just a real quick example of how evidence might change the result. So here we're querying over the probability of x being in state 1 as time goes on. Well, we know that x is in state 0 to begin with, but we see that as time goes on, it becomes more and more likely that x transitions to state 1. Well, the blue line here is if we apply evidence that says A is in state 1. But then if we say B is in state 1, we end up with the red trend here. And then if we say C is in state 1, we end up with the green trend. There's no way to understand the dynamics of this without going in and looking at the individual parameters. This is simply intended to show you that as you apply evidence, your expected probability for any sort of query is likely going to change. All right, so we can get into the second paper. They're going to use a variational method, and a variational method is basically just going to approximate the true distribution with a simpler distribution. And it's then going to perform inference over that. So performing inference over the true distribution is NP-hard. We're just going to approximate that true distribution with one that's a little more manageable. And we're going to do that by restricting the set of densities to a manageable class. And we're only going to do that by only looking at densities that can be factored into a product. So again, it's much like how we've been factoring things in the past. We'd like to be able to factor this out so that things become a little simpler. And the way they're going to try and best approximate the true distribution is they're going to look at that subset of simpler distributions and then pick the one that is closest to the true distribution. They're going to measure closeness with a metric called tail divergence, and that's just going to simply tell us how similar it is this distribution to the other one. So, a little bit of background here. The prior distribution of a CTBN is a homogeneous Markov process, and all that means is that the intensity matrix is not going to change as events occur. So as you continue along the inference process, the intensity matrices stay the same. The concern is that the posterior distribution, so that's after you've applied evidence. As soon as you've applied evidence, we're not necessarily dealing with a homogeneous process anymore. So what we'd like to do is we'd like to use that concept and say, okay, well, let's approximate this with an inhomogeneous Markov process. So we've been dealing with homogeneous ones where all of the Q values in our intensity matrix are going to remain static. Well, now they're actually going to use, instead of an intensity matrix, they're going to use what's called a rate matrix. And so we're going to call this R instead of Q, and it's actually going to have values that change over time. And we're going to build this using the sufficient statistics of a CTBN. And the sufficient statistics are just going to be, this you can gather from just counting. It's going to be how long you spend in each state, and it's going to be how many times you transition from one state to another. And if you collect all that information, you're actually able to parameterize the entries in the rate matrix. We have one concern, and the concern is that you can't have infinite values in your rate matrix. And as you approach evidence, let's say you know that a variable is in state x1 at some time in the future. As you approach that time, if it's not currently in state 1, your intensity for transitioning to that state goes to infinity because it has to force that transition to occur. So this ends up causing us to go to infinity. To make everything valid, and there were quite a few proofs that went along with this, but they came up with a set of constraints that's going to create valid mu and gamma function or gamma values that are going to allow us to parameterize the rate matrix. I'm not going to go over the details of how they came up with these constraints, but the important thing is we have this set of constraints, and we would like to minimize the tail divergence between this and the true distribution. So what we got is a constraint optimization problem. At this point, just because we've got this rate matrix, it's no easier to perform inference over. So what they're going to do is they're going to simplify it by factoring it into independent processes. Basically what they're going to do is they're going to go variable by variable, and they're going to fix the states of all other variables in the system. And they're then going to perform this constraint optimization problem. They're going to find the optimal value for that variable, and then they're going to move on to the next variable. So they go variable by variable. This is the factored notion of this. This is where it becomes tractable. And what they end up doing is they fix all of the states, optimize for that variable, and then move on to the next variable and do the same thing, and all of a sudden, this problem is actually feasible. The way they're going to do their optimization in this paper is they use a set of ordinary differential equations. They use the Lagrangian method, but it really doesn't matter how you do the optimization. You could use any sort of optimization that would actually do this job. So, for this paper, they defined a set of inhomogeneous Markov processes. Those are the rate matrices. And this set was actually, it was easy to perform inference on. And so they searched that set to find the best approximation of the true distribution so that the result they're getting out is actually very similar to the result you get out if you did inference exactly. One open question is what about non-exponential distributions? So these matrices we've been talking about, the rates in the matrices define an exponential distribution. So it's the rate for an exponential distribution. You can actually provide an extension. There's an extension called phase type distributions, and it's essentially another Markov process that you embed within the individual cells of the matrix. So for each Q, there is a cell of that consists of a whole other Markov process, and this is going to actually approximate a more complex distribution instead of an exponential distribution. Phase type distributions are themselves inhomogeneous Markov processes. So if you are using phase type distributions to approximate more complex distributions, the question is left is that is there an informed way to construct these rate matrices based on the structure of the phase type distributions? Because we've already got subsets of the matrix we're working with that are themselves inhomogeneous. So there may be a more efficient way to construct these matrices. Okay, so that was a variational method to perform inference. Now we're going to take a different approach, and we're still going to be looking at an inference algorithm or CDNs, but we're going to be looking at a sampling method, which is going to be fairly different in terms of their approach. So for a sampling method, the general idea is to sample from the target distribution and then use those samples to answer your queries. So you've taken many samples and you end up with hopefully a fairly large population where you can actually compute the statistics from. And the nice thing about this is it's an anytime algorithm. So what that means, for those of you not already familiar, is that as soon as we've got even a small number of samples, we can compute statistics for it. So almost immediately, if someone wants a result from the query, we can return it. Now, with a small set of samples, it's probably not going to be very accurate. Of course, as we collect more samples, it's going to get better and better. But the nice thing is, for the variational method that we just looked at, you have to wait till it's finished. Here, you can return at any point. So, in terms of sampling, sampling from a prior distribution is fairly simple. In a CTBN, it's called forward sampling, and all it is you go through the exponential distributions defined by the rates, and you just walk through and sample from the distributions and take the variable transitions that end up occurring. And so you just follow the behavior that is defined by the CTBN. What you end up with is a set of samples, and you're able to compute your statistics, and everything's fine. The concern is, as soon as you apply evidence, this doesn't work quite so well anymore. So if you apply evidence, then if you just follow the CTBN and you sample from the exponential distributions, there's no guarantee that you're going to end up in the correct state that's going to align with the evidence. It's not going to conform with the evidence necessarily. So there's a couple different ways to handle this. The natural way, especially in Bayesian networks, is rejection sampling. So the concern is if you sample and you get to a point where you've sampled and you end up in a state that does not conform with evidence, like you're talking about, you just throw the sample out. And so that sample's gone, and you try it again, and hopefully you don't end up throwing too many of them out, and in the end, you end up with, it takes a little longer, but you get the same amount of samples in the end. The concern is that in continuous time, it doesn't work in general. And the idea there is that there's transition evidence. If you're transitioning at a discrete time point, say, let's say at time 5, you transition from x1 to x2, well, the probability of that exact transition occurring at that exact time goes to 0, because we're working with continuous time. So rejection sampling just doesn't work with transition evidence. So instead, we're going to look at importance sampling. Here, you're actually going to sample from a proposal distribution, T prime. So we're not going to sample from the true distribution anymore. We're going to sample from some proposal distribution. And we're going to construct the proposal distribution such that it's going to guarantee that when we sample, it's going to conform to evidence. So now we don't have the issue of potentially sampling and getting something that does not align with evidence. We're actually going to force the distribution to provide us with samples that conform to evidence. The concern is we're not sampling from the true distribution anymore. So we're going to compensate for this by computing a weight associated with each sample that considers how likely it is to transition or to sample from the proposed distribution as from the true distribution. And so that's going to provide an offset that accounts for us sampling from the wrong distribution. For this, they defined what they call simple and general evidence, and they show how we can construct this proposal distribution for each case. And so for simple evidence, they talk about that being, okay, you've got one variable and you know its states from the very beginning of time until the end of the time you're looking at for inference. So you know what this variable is doing all the time. That's fairly simple. If you know what state this variable is in all the time, then you're just going to sample from p prime and compute the likelihoods for each of the transitions that are occurring, because you know exactly when those transitions are occurring, and you can compute that likelihood of that transition occurring in the original distribution, and we've got a simple weight calculation from that perspective. The concern is when you've got general evidence, things get a little trickier. So general evidence, they consider you don't know the state of a variable at some points, and you do at other points. So let's say from time 0 to 5, you don't know what state x is in, but from time 5 to 10, you know it's in state x2. Well, we should be allowing it to behave however the distribution should allow it to behave from 0 to 5, but we're going to have to force it to transition to x5, or x sub 2 at time point 5. The concern there is that if you've got multiple points of evidence at time 5, if we instantaneously transition it at that time point, it's actually going to cause instantaneous transitions of two variables, which you'll remember back is not allowed. Yes. So to fix this, what they did is they sampled from truncated exponential distributions. So they say, okay, I don't know what variable x does, but I know that it has to transition to x2 by the time I get to 5. So it says you can transition anytime in between now and then, but it has to be at least by then. And so that's what it's going to do, is it's going to force a transition to occur by that time. They have a couple different extensions. One of them is going to provide us with predictive look-ahead, is what they call, and basically the idea is that even though you can force it to transition by that time, it doesn't tell it which state to go to. And so what might end up happening is it might end up jumping between states very quickly to try and align with the correct state, nearing the point of evidence. So this tries to intelligently pick the state. And then second, they have something called particle filtering, and the general idea here is that samples are drawn consecutively in the traditional algorithm. This allows you, the particle filtering allows you to draw them in parallel, which is great for online. So, importance sampling. The idea is we create this proposal distribution P prime. We draw from P prime instead of P, and we weight it to compensate for this. And then what we end up finding is that, well, it's an anytime algorithm, which is useful on its own, and it can be more effective than variational methods. The main benefit to variational methods, the one we just looked at before, is that they're quite a bit faster in terms of getting a very good solution. But if you let importance sampling run, because it's a sampling-based algorithm, if you let it run long enough, you end up with more accurate answer in the end. So, some open questions here are that one concern is, remember, it's no longer exponential in the number of variables in the system, but it's still exponential in the number of parents that you have. So one way to mitigate this is to use what's called noisy OR node. This has been proposed for Bayesian networks. It can also be done with CPNs. But the general idea is, instead of having to define one for each state instantiation of the parents, we're actually going to change that from exponential to linear. we're going to have to just define a conditional dependency matrix for every event where one parent is in state x1 instead of every possible state in the here. So the question is, with the presence of this noisy OR node, is there a way we can use this with importance sampling? And if we can we actually take advantage of the fact we're using a noisy OR node and improve the computational complexity of importance sampling if we've got these noisy OR nodes in there? Okay, so we've got our model, we know how it looks, and we know how to infer using a couple different methods now. But the concern is, what if we have more complex knowledge about the states in our system? So we may know that a variable is in a particular state at a particular time, but we also might have more complex information that we've learned. Maybe we know it's in a particular state with some confidence value, or maybe we know that it's not in one state, but we're not sure which state it is in. So this next paper is going to look at all the different possible ways to provide information to the model so that we can then infer over the network. And I'm pretty much going to spend the entire time talking about this paper looking at this beautiful graph right here. It's going to summarize the entire contribution to the paper. These are all the different types of evidence that we can use in CPBN. We've got three main different types. In the top right, we've got point evidence. This is the idea that we know at a discrete point some information about the model. In the bottom right, we've got transition evidence. This means at a discrete point, we know about a transition that occurred in the model. And then on the left, we've got interval evidence. And this is saying, instead of for a discrete point, we're saying for this entire time interval, we know some information about the model. The solid lines here are going to represent a relationship where the parent is a special case of the child, and the dotted lines are going to represent one where the child can be used to approximate the parent. Okay. The first one I'm going to cover is I'm going to cover this point block up in the upper right. So we're going to start with certain point right there, and this has been defined already for CPBNs. It's been used in the past. And it's the notion that at a discrete time point t, I know that the variable x is in this particular state x1. So you can say, I know the exact state that this is in at this particular point. Negative point evidence is going to say, I know at this exact point t that the variable is not in this set of states. So you can rule out some set of states from the possible states, but you can't actually determine which state it is exactly. And then finally, we've got uncertain point. And this is the notion that you know that it's in a particular state at a particular time, but only with some confidence. So you can say, I know that there's a 90% chance that variable x is in this particular state at time t. So negative and point evidence are both new. These were introduced in this particular paper. Okay, we're now going to move on to transition. So we've got certain transition, similar to certain point. You know that at a particular time t, that it was in one particular state, call it x1, and it's going to a new state x2. So you know where it's coming from and you know where it's going to. So those are known values. Negative transition means that you can rule out a set of the values that it's transitioning from and to. And then uncertain transition is, again, the concept that, okay, I know it's transitioning from this state to this state at time t, but I'm going to assign a confidence value associated with both where you're coming from and where you're going to. So I know with probability 70% that it's coming from state x1, and with probability 90% I think it's going to x2. We've also added, and this is a little trickier, we didn't have this for point, we've got temporally uncertain transition. So you can be uncertain about the states that it's coming from and going to, but you can also be uncertain about the time at which the transition occurs. And so you can say, I know that it's coming from this state to this state and I know it's going to happen within this time window. And there's going to be a uniform probability of it occurring throughout that time window. That just leaves us with interval evidence. The main points here are we've got certain interval evidence. This again existed before the paper. And the idea is you know that for a particular period of time, from T1 to T2, that a variable was in a particular state. Then we've got negative interval. From that period of time, you know you can rule out a set of states. We've got uncertain negative interval evidence, which is going to be a combination of the two. We're going to say that you can rule out a set of them, but only with some probability. And then we've got uncertain positive interval. And that means we're going to say, with some probability, I know that this one particular state, it was in this one particular state for this time window. It can be a little complicated, but the important parts to take away here are that certain point, certain transition, and certain interval all existed before this paper, but there was no method for applying more complex information. So all these other points of evidence were introduced in this paper. Furthermore, every link you see here is a proved relationship. So there's a proof that says that you can actually approximate these things. So as an example, certain interval is a subclass of uncertain positive interval evidence. It's just a very specific case. It's one where you set the probability to 1, right? And we see that uncertain point evidence can be approximated using uncertain positive interval evidence. And that's because we can approximate evidence occurring at a particular point by making the interval very small. So as the interval approaches 0, then we're ending up with what is essentially a discrete time point. And so that's important information to gather from this. Hopefully, this should clear some things up if you're still just a little lost. The idea here is we've got point evidence on the left, transition evidence in the middle, and then interval evidence on the right. And what we see is that there are various samples that we can draw that will conform to this evidence. So even though we've got this evidence and we know about states in the system, we don't necessarily know, we can end up with different sample paths that end up conforming to the same types of evidence. I apologize. What time am I done here? Is it off the hour?
Well, should be now.
Okay. I will wrap it up. So the last paper we're going to look at is sensitivity analysis. How do variations on the input affect its output? The input in a CTBN is changes to the initial distribution and changes to intensity matrices. And we're going to look at how this affects inference. So how do changes to our intensity matrices affect how our inference results are going to come out in the end? The way we're going to use this is perturbation realization. It has been proposed for Markov processes, but basically it's going to look at how changes in the steady state distribution of the process are going to change the results. And so you can calculate this by taking a really long sample, or you can take the eigenvectors of the intensity matrix and get this in a closed form. So you could just amalgamate the entire CTBN. That means combine it back up into a Markov process. But it doesn't factor the process, so we're going to end up with something that's too complex to reason over. So what we'd like to do is we'd like to perform node isolation, which is going to replace all of the conditional intensity matrices. So we've got a set of conditional intensity matrices, and we're going to approximate it with just one matrix. So we lose some representational power there, but we've got one matrix. And now that we've got one matrix, we can then do our sensitivity analysis using our perturbation realization using that one matrix, because it's already been defined for a Markov process. So what we can do there is we approximate the set, we then add a perturbation matrix, we call it a perturbation matrix Q, so we add the values, and we basically measure the difference in the output after we perturbed it. And so what we end up with here is we can calculate the difference by taking the steady state multiplied by the perturbation matrix, and we'll then multiply that by our expected output for each state. And this paper introduced sensitivity analysis for CTPNs. I didn't do it justice because of the time constraints, but the basic idea here is that we've dealt with inference and we've dealt with our evidence, but this is going to allow us to perform the task of modeling a little bit better. So this is going to allow us to determine whether or not changes in our model are going to affect our output. Some open questions here are, again, is it possible to incorporate base type distributions, and can they be used to approximate a set of conditional intensity matrices for the node isolation process? In my research, I am working on noisy arm base type distributions, and I'm trying to reduce inference complexity using noisy OR, and I'd like to be able to use sensitivity analysis, the last thing we were discussing, to identify candidates for performing noisy OR, or for replacing nodes in the network, normal nodes, with noisy OR nodes. And then last, I'd like to look at base type distributions, and specifically, I'd like to look at how they can be used to approximate a set of CIMs, conditional intensity matrices, with a single intensity matrix. So far, I've published a few papers in this area. I've got 3 papers that I've published so far, and I am in the middle of working on some already. One's already been submitted, and the other ones, again, deal with base type distributions and noisy OR. So this is a major direction for my research. Okay, thank you.
Any questions below? About 4 minutes left. Then you'll probably save their questions for you.
Does that make sense?
All right, let's thank Logan again. We'll wait until the top of the hour. So, private session.